you could add it to the matching, and the matching is not maximal. Okay, so each of the edges of the graph is covered by these 6 blue vertices, light blue vertices. Now, what can I say about maximal matching? Okay, what can I say about about optimal cover? The optimal number of vertices that cover all the edges. By the way, you don't have to take picture of this. I can send the slides to Professor Tomare. Everyone can share the slides after the conference. Yeah, with pleasure. Now, since we have to cover these 3 independent edges, vertex cover must be of size of at least 3. On the other hand, if we take all the 6 vertices, we cover all the edges. So the optimum must be at least 3, but at most twice 3. So this gives you a 2 approximation. This is the first example that you see in class of approximation algorithms. So this is an idea of approximation. I give you a very small idea. To find the maximal matching, you do it in linear time. You just go edge, edge, and greedy, very easily you find a maximal matching. And in linear time, you find a vertex cover, which is, it's not optimal, but it is at most twice the optimum. So this is a 2 approximation for the vertex cover. Okay. Now, why do we need online? What is online? Online is when I don't have all the input in the beginning. I don't have enough information. And in networking, it happens a lot that I give you the information one by one, and you have to find a way to do it. In scheduling, for example, I give you, a job comes, you must schedule it to a Sun machine. Another job comes, you have to schedule it, no matter what the constraints are. And then you cannot change your decision. But here, since the input is given online, we can only approximate an optimal solution, okay? I'll give you an example in a minute. What is competitive ratio? An algorithm for minimization problem is alpha competitive if it always satisfies alg not more than alpha times optimum. It means that the solution is, okay, I'm using alg also for the name of the algorithm and also for the value of the algorithm, okay? The value of the algorithm is not more than alpha times the optimum. Let me give you an example. And this is again the first example from book online. And this is a very tricky example. Okay, you go to ski. Now, you say, I never skied, I don't know if I like to ski. So I can stay 1 day, 2 days, 3 days, 20 days, I don't know if I like it. But you don't know if you have to rent or to buy the ski, because you never skied in your life. Now, if you buy the ski, then you pay $10. If you rent, you pay only $1 per day. But you don't know how many days you are going to ski. So what do you do? What is the best strategy? Now, this is an online situation. Why online? Because after the first day, only you decide if you stay for the second day. After the second day, you decide if you stay for the third day. You don't know ahead of time how many days you are going to stay. Okay, so it turns out that the best strategy, you buy the ski on day number 10. So if you ski only 8 days, you pay only $8 because each of the day you rented a ski. Okay, if you stay 10 days or more, then you buy a ski. And if you make the analysis, you can show that this is 1.9 competitive. So you never pay more than 90% of the optimum. Okay? And the 1.9 comes because it's 1 minus 1 over 10. If you change here 10 to 25, this will be 25. And the solution will be, if the ski costs $25, then you buy the ski on day number 25. And you can prove this is the best you can do in the worst case. So, and then, if you don't want to pay more than so and so times the optimum, this is your best strategy. Now, the first example that I show you with the vertex cover is very easy. This is very tricky to prove. Try to prove it, it's a nice exercise. But this is really like one of the first problems that you see when you take a course on online algorithms. Okay? So this was just a tip tip of the iceberg, what is approximation algorithm, what is online algorithms. Okay. Now, okay, I'm going to skip the list. The talk is based on some papers of mine, but I'm skipping the list. Okay. Second thing, now what are the problems? The problems are the following. We start if you speak about third generation optical networks, the optical fiber was served only as a transmission medium. I guess some of you in electrical engineering know about it, but I'm not going to use it anyhow. Just to say that when you speak about second generation, when the routing is done in the optical domain, and then people have used two complementary technologies, and these bring us beautiful problems that I'm going to show. One is wavelength division multiplexing. Okay, you can do transmission of data simultaneously at multiple wavelengths over the same fiber. And then optical switches, the switching of the signal is done by optics, by mirrors. We don't have to know anything about it. I'm not going to say anything about it anymore. From my point of view, the problems are only graph theory and algorithms. Now, what is a light path? A light path, this node, to communicate with this node, it has to establish a path in the network, and the path is going to be colored by some wavelengths, let's say red. Now, the basic thing is valid coloring. If I have to use this path and this path, since they are here using the same physical edge, they must get different colors. Okay, one red, one blue, for example. Now, there are 3 points that we're going to optimize. One of them is ADM. ADM, add drop multiplexer, but I don't need its use. In the beginning and the end of each light path, I'm using this box. Now, what is my cost? And this is the first question. Here I have physical cycle with 1, 2, 3, and 4 light path. These two I decided to color blue, this one red, this one green. So altogether I'm using here 8 ADMs. But I want to save on the ADMs. What I can do, I can make this red, okay? I can make this red blue. And by this box can be used by both. And this is where I can save. So the first problem is, I want to color the path, and when they meet, I can save one box. So the optimization problem is to color the path and use as small number of ADMs as possible. Okay, this problem became very, very practical, and it has many applications, but I cannot get into the area now. So think about the graph. Forget about optical networks. Think about the graph. In the graph you have path. Each path has to be colored so that when two paths intersect, they cannot, if they share one edge, they cannot get the same color. So each path is, I have 100 paths. Each path needs 2 boxes, so altogether I need 200 boxes. Where can I save? If I color this path and this path red, and they meet at one point, and altogether they make one continuous path, then I can save one box. So altogether, I can save many boxes. Second problem is about the generators. Okay, the light path is used for communication between pairs of nodes, like this light path. But when the light path goes, the energy decreases, so we have to use amplifiers, okay? But the amplifiers introduce some noise, so we need to place some regenerator. Okay, the Popeye is going to be my regenerator, and once I put in some regenerator, this is some optical device that makes the signal stronger, so when it gets to the end, it will be strong again. So regenerator is just some device that I have to put on the way to make the signal stronger. And in terms of of a graph, okay, so what do I mean here? In terms of graph, I have a path, and each few steps I have to put a regenerator. So again, forget about optical networks, I have a path, and along the way I have to put some regenerators to boost the signal. Now, here, for example, suppose B equals 3, I need to put a regenerator every third node. So here, 1, 2, 3, I must put here a regenerator. I cannot pass more than 3 nodes without putting a regenerator. So in this example, I can put here and here a regenerator, and those 2 regenerators will be okay for this signal. Okay. Now, yes. If you want only to minimize the number of regenerators, then this problem is easy, because if I have one path, for this path I have to use 2 regenerators. For the blue path, I have to use the blue regenerator, and for the green path, I have to use the green regenerator. Here, D equals 3. So every 3 points, I cannot pass through 3 points without a regenerator. So the minimum number is 4, and this is easy. But very difficult problem, I'm not going to talk about it, but I will talk on a similar problem, is the number of locations. It turns out that if I want only to minimize the number of locations, in this example, I can put here a regenerator, to put here 2 regenerators, one for the red and one for the blue, and to put here also 2 regenerators, one for the blue and one for the green. So I use only 3 locations. Okay, I use more regenerators but less locations. So there are many, many optimization problems here that for students who are looking for, but we have a lot of papers also about this, but I will talk about a problem which is slightly different from this in a few minutes. This will be topic number 3. Now, yeah. So we have 2 cost functions so far. One is the number of boxes, ADMs, at the end of the light path. The second is number of regenerators at the middle of the light path. Now there is a third problem. Okay, I'm not designing only top level, and when I come to specific 3 examples, I'll tell exactly what I'm doing.